Good morning to all of you. So today I thought of first let me discuss some conceptual questions of minor 2 and then I will continue further. Meantime, if you have any questions you can ask. So are there any questions? Okay, so let me, although I mean some of you would have done, so for some of you it might be trivial, but let me discuss that. Maybe the answer books would be distributed next class. So let me question 1 was actually on locking. So what I had said was that in a curved beam element, so of course they can also be modeled using straight elements. So suppose if you have a curved beam structure like this, so you have actually, although it's not necessary to solve the problem, but actually what is done here is a curvilinear coordinate is taken. So say this is x and normal to this if it is z, x is actually at any given point is tangent to the centroidal axis of the beam. So here x would be like this, here x is going to be tangent like that. So for this it was given that the strain epsilon xx, normal strain along x direction at any point having no coordinate z is given by du naught by dx plus w by r. So u naught is the displacement of the point on the centroidal axis, that is any point here along x direction, and w was the displacement in this direction, and plus z into d theta by dx, and theta is the rotation about z axis. So no, not about z but about negative y axis as per this coordinate system. So I had said that r is a known constant which is a radius of curvature, that is this particular r, and other variables are functions of x. So u naught is a function of x, w is a function of x, theta is a function of x. Thin and shallow beam elements depict membrane and shear locking. So in addition, of course, you also have the shear strain which is gamma xz given by dw by dx plus theta. Here theta is rotation about negative y axis, so that is why you see a plus sign here and similarly a plus sign here. So now membrane locking meaning is actually because of this term which I had mentioned, and since I had discussed in the class about shear locking, so I left that for you to interpret. So now what it says is if a beam is thin, then for thin beams, for thin means the thickness is much smaller compared to the length, and shallow meaning is that it has a curvature. So if I look at the whole beam, this is just part of it, so no, it has certain thickness like this. So if I look at from say horizontal, this height, the central height of that, let us say this is capital H, and small h is, let us say, the cross-sectional thickness of the beam. So if this h is much smaller, then the beam is known as shallow beam. Means it has a curvature, but know that height from in points to the central point, that is maximum deviation h, but it is much smaller. So it has a curvature, but it is more like a straight beam, but it is not straight, has some curvature. So we call such beams as shallow beams. So thin means this small h is much less compared to length, and shallow meaning is that this capital H is much smaller compared to overall length of the beam. So the beam is thin and shallow, and for that I had written so membrane shear locking, you already know that gamma xz for thin and shallow beams, gamma xz would approach to 0. In addition, I had mentioned that the membrane strain approaches to 0. So membrane strain is this part du naught by dx plus w by r, this is approaching to 0, and this leads to transverse shear locking, which we had discussed in the question. I had described that if this approaches to 0, we also have what is known as membrane locking. So what should be the interpolation of u naught, w and theta, so that no element does not depict locking when this is used for shallow and thin beams. So since we had discussed, so I expected you that you would be able to actually extend this concept of transverse shear locking, consistent interpolation, also to the membrane locking. So first thing is, say that now when you look at the interpolation, of course the basic requirements have to be met. So for example, if you look at theta, all the variables in the strain energy expression, because no, they are first derivatives of u naught, du naught by dx, d theta by dx, dw by dx, first derivatives are appearing, so at least they must be differentiable once. And here also u naught, w and theta are going to be basically primary variables are the problem. So the minimum requirement for each of these variables is linear interpolation within the element. So that means the curved element can be basically minimum is two noded curved element. So node 1 and node 2 with each node having u naught, w and theta as the degrees of freedom. But that will give you, say for example, if you look at theta as, say, let me start with theta. So a0 plus a1x, where x is the coordinate in this direction, and then w will be, say, b0 plus b1x, and then u naught will be, say, c0 plus c1x. But this is the minimum required interpolation approximation of these field variables, but this will lead to locking. So then what we do is we want to have consistent interpolation. That means when we look at the gamma xz, the interpolation of theta and dw by dx must be consistent. So the consistent interpolation means, now this is minimum. When you look at the consistent interpolation, what we want to have is the same order of interpolation for both the terms in each of these constraint strains, that is gamma xz and the membrane strain given by this. So if theta is linear here, which is minimum, we cannot take less than that. That is, constant theta is not acceptable, because then its first derivative will not exist, which is required here in the strain and therefore in the strain energy expression. So minimum is that theta must be at least linear. So like what I just wrote, a0 plus a1x, and then since w is here in the gamma xz is appearing as first derivative, so w must be quadratic, so that dw by dx and theta, they are consistent. So then w means should be actually b0 plus b1x plus b2x square. So this is coming from, if we have this interpolation for theta and w, the element would be free from shear locking, because then we have the consistent interpolation of gamma xz, that is order of interpolation of theta and dw by dx is linear. Theta is already linear, and since this is quadratic, dw by dx will also be linear. So there would be no spurious constants leading to locking, that is leading to underprotection or deflection. Then for membrane, now if you go, the other strain component, this du naught by dx plus w by r. So see, again we have already based on the transverse shear strain, we already said w should be quadratic. So now if this is quadratic, and we have this du naught by dx again, so for this to be du naught by dx to be consistent with w, du naught by dx, u naught must be actually cubic polynomial. So that du naught by dx is quadratic, and this term quadratic, this is also quadratic, so they would be consistent. And it can approach to 0 without any of these individually being enforced as zeros. So then finally you need to have u naught as cubic, which is, say, c0 plus c1x plus c2x square plus c3x cube. So this is what actually I expected you, that you say that minimum required is linear. Of course theta we can take that, but then for the consistency we need w to be quadratic and u naught to be cubic. And since u naught, w and theta are primary variables, so now finally when you look at the degrees of freedom, so this is a curved element, I am just talking about only one element. So theta has got two unknown constants. So we can have theta as the degrees of freedom at these two in nodes. So this is node 1 and this is, say, node 2 first, let me say. So theta 1 is 1 degree of freedom here, theta 2 is another degree of freedom here. So these two degrees of freedom can be used to represent a0 and a1. Then w has got 3 constants. Now 3 constant means there must be 3 degrees of freedom corresponding to w. So one we can have here w1, here we can have w2, that we have to ensure the continuity of w across the elements by taking the same values of theta and w at the common node between two elements. Then we need a third node, so we can have intermediate node here. So let us say that's the third node, and here we will have degree of freedom as, let us say, w3, but no theta degree of freedom at third node. So only w, so w is degrees of freedom w1, w2, w3, Now in terms of these W1, W2 and W3, we can write B0, B1, B2. So we will have corresponding shape function which would be quadratic. Now if you look at U0, so U0 again is a primary variable, so we can only have that as degree of freedom. So I can of course have U1 here and U2 here. We have to have that. That is value of U0 at 1 is let me say U0 1 rather than just U1 and U2. So this is U0 1 and this is U0 2. Then we need 2 more because we have got 1, 2, 3 and 4 constants, and that means we need to introduce 2 more nodes. So see, maybe then again you can think of whether we can have U here as a degree of freedom, but usually unless and until, like I was talking about inverse square singularity, we try to place the elements at equal intervals. So node 3 we are using only for interpolating W, whereas for U we need another node. So let us say this is node 4 and this is node 5. So this distance would be 1/3, 1/3 and 1/3. So that the node 4 and 5 are equally spaced from the ends of the element, and 3 is at center. And here then we will have say U0 4 and U0 5 as the degrees of freedom for U. So again corresponding to U we have got 1, 2, 3 and 4 degrees of freedom. So these 4 constants can be represented in terms of these. So this will be the corresponding actually element. So now if we have this kind of an element, curved beam element, it will not have any locking. It can be used for thick as well as thin beams. It can be used for deep curved beams, or it can be used for shallow curved beams. So deep means something like the included angle is much larger, whereas here the included angle is very less. So this is what I actually expected you in fact is to do this, which was a straightforward extension of what we had discussed for the transverse shear locking. So including membrane. So this is what additionally you had to do. Yeah. No, you cannot have that at in nodes, because in nodes you already have U0 1 and U0 2, and those will be used to enforce the continuity of U0 across the elements. So these are going to be at intermediate nodes, U0 4 and 5. They cannot be, even one can think of something like here having derivatives du0 by dx at node 1 and 2, but then they are going to be secondary variables, and sometimes there might be a concentrated forces acting at the nodes. So then they will not be continuous. So you have to have then additional degrees of freedom at the same common node. Of course, sometimes we do have to have that, but here preferable is that you have at intermediate nodes the additional degrees of freedom. Although this is more complex element, so there are other methods of, as one of them was actually reduced integration for eliminating transverse shear locking. So similarly membrane locking can also be eliminated using reduced integration. So element is obviously, as you see, different nodes having different degrees of freedom. So in nodes I've got 3 degrees of freedom, then we have one node at center which has only 1 degree of freedom, that is W, and we have 2 more nodes which are having only degrees of freedom U0. So it's more complex of course, and usually you don't find such elements in software. So if you're developing your own code, you can obviously do that and can study the problem. So this was one. I think the question 2 was straightforward. Only thing what I want to mention is I don't want to solve the entire problem, but see, I did not say that whether 2 displacement or a single displacement. So some of you of course have done it correctly, but see, what I had said was that this is x and this is y, this is node 1, this is node 2 and this is node 3, and I had given basically a distributed load along this. So I think if you look at the diagram, it was clear that load is along the x direction, that is horizontal direction. In addition, I had said that this is qx, which is given by 100 into x. So I had asked you to find out the load vector for this. The coordinates of various nodes were given. This was 0, 0, and node 2 was this was 1 and 0.5, and this was 0, 1. So one is whether it is this obviously the load. So it's a mechanical problem, solid mechanics problem. Now the question is whether it is a 1D or a 2D. So if you see the dimensions, this direction, the length is 1 unit. I think I didn't say any units here. Of course, with the force I had said Newton per meter. So the coordinates are also in meters. So this is 1 meter, and this direction also it is 1 meter. So the 2 dimensions are comparable. So obviously this cannot be a 1D problem. It has to have be a 2D problem. So 2D means, and the load is then in the in-plane direction, in the plane containing the structure, so it can be a plane stress or a plane strain. So when you talk of a load vector due to this distributed force on an edge, you will have to consider a 2D problem, not a 1D problem. So some of you just took it as if no, it's a 1D problem, and we have only one displacement component along the x direction and try to work out the load vector, which is not correct, no, because you see the dimension, this side and this side, the two dimensions are comparable, and the load is acting only in this direction. So you obviously expect that it will of course stretch in this direction, it will also have some displacement in this direction. So that is what I expected. We had discussed that, when we use two-dimensional elements, under what condition, what are the constraints on dimensions and so on. So when you look at that, only load is this and there was nothing else given. So the load vector, whether you want to call it as external or internal, which is a known load. So load vector for the element is basically going to be, we have already done that H transpose into Q, the integration is going to be along this edge. So integration along edge 2 to 3, this is H transpose. One force is Qx, another direction the load is actually 0, which is Qy, and then this is ds. So H transpose here is, now it's a triangle. So of course you had two options, because we had also discussed that triangular elements can be derived from four noded isoparametric element also. So you can derive the load vector from there, but in this case it was your choice. It is easier to use the area coordinates in this case. So then you have three nodes directly, and therefore your H is simply going to be L1 0, L2 0, L3 0, and then 0 L1, 0 L2, 0 L3. So this is your H. So that the first row into a vector of elemental degrees of freedom U1, V1, U2, V2, U3, V3 give you U, and the second one gives you W. So this is your H, and Qx is given as 100x, Qy is given as 0. So you multiply this and then do rest of the calculations. So you can write L1, L2, L3 as the ratios of areas as we have discussed in the class, and then you do the integration. Now that integration is going to be along the edge. Again, see, some of you just try to write it, because when you go either 3 to 2 or 2 to 3, because x and y both are changing, so you just wrote it as double integral. See, the load is acting along an edge, so it has to be a line integral, it can't be an area integral. So then you have to do a line integral. So if you are going from 2 to 3 the way we discussed, so you have to take a ds here, and that ds is going to be of course square root of dx square plus dy square. You can take one of them out, say dy by dx whole square and then dx. But in this case, if you are going from 2 to 3, so x is decreasing, but s is a length, so it must be positive, so you put a minus sign here. If you are going from 3 to 2, so then ds is equal to this into dx. That will take care of the sign in the load vector. Finally, it has to be basically positive load vector. And then of course you can write the equation of this line 3 to 2 and express y in terms of x. So finally in H transpose Qx Qy you will have everything in terms of x, and ds is written in terms of dx, and you then do the integration. So that of course I have also sent you the link for the solution. You can have a look at further. Conceptually I wanted to discuss that what you should have thought about doing this problem. Maybe the question paper was little lengthy, although I had given 10 minutes extra. But at least whatever problems you do, at least in that there should be some thought process, that what should be done and why should be done. So this was what I actually expected in question number 2, and 3 is 3 was also a straightforward question, because we had discussed a lot about inter-element continuity requirement, that is compatibility. So only thing this was slightly different, that I had said that we have assembly of two elements, one is 8 noded and another is a 4 noded element. So like this. So we have the 8 nodes here for the first element and 4 nodes for the second element. So this node here, there is some numbering scheme here. So 1, 2, 3, 4, then I had said 5, 6, 7. No, sorry, the 7 is not there. No, this, yeah, 7 is at the top. So this is 5, 6, and then 7, 8, 9, and then we had this as 10. So for node 6 is used only for defining the displacement field in the first element. So this is element 1, this is element number 2. I ask you to sketch the distribution of field variables, say u. So if it's a solid mechanics problem, the displacement along x direction is, let us say, u. So one is, of course, some of you try to take this line from A to B as a general line, although the way I had sketched, you can easily take it as a line with, say, x is equal to constant, the way I had discussed, but even it doesn't matter. Even if you take it as a general straight line, then also it's fine. So if you look at, you can argue out in any manner. Say if you use, let's say, the the interpolation in the physical coordinate space, because the elements are rectangle. So otherwise, use of physical coordinates is okay for satisfying the inter-element compatibility requirement. So for first case, we will have u as for this 8-noded element, a naught plus a1x. Many of you actually did this question, of course, a2y plus a3x square plus a4xy plus a5y square plus a6x square y plus a7xy square. Now if you take, if you are looking at variation of u along AB, so wherein your x coordinate is constant, so you will find once you put x coordinate constant, this would be something like a0 plus a1 y plus a2 y square. This is what is going to be this form when you put x is equal to constant in this, because there is a linear quadratic linear term, constant term, and a quadratic term of y. Even if you take x is equal to some general equation of a straight line a naught x plus, a general form also, then you will have, of course, this as cubic, the other one would be quadratic, still you will have a mismatch. So this is for the first element. Now for the second element, so element 2, UAB then would be, because you will have, if you look at the polynomial for this, is going to be, say, some b0 plus b1x plus b2y plus b3xy, because a 4-noded element. So we have 4 degrees of freedom corresponding to each variable for the second element, so only 4 terms. So this variation would be something like b0 plus b1 into y along x is equal to constant. Here x is constant along AB. So now this is quadratic, this is cubic. So if you in general look at the displacement distribution, of course it's not necessary that at A and B, at these 2 points, the values of u are 0. So they can be any non-zero value. Say you have some value of u here, some value of u here. The second element is going to give you just a linear element, a linear variation. So this is variation from the second element, but this is quadratic. And for that element, you will also have some value at node 6, that is center node. Maybe let us say that value is there. So within the second element, the first element, this variation would be like this. So this is coming from first element, and here this is your y, and this direction is your u. This line, this point A and this point B. So as you see, at point A and B, the 2 elements are giving you same value of u, the field variable, but in between of course a general case, what we are talking about, a general case. So in between the element 2 is giving some value of u, whereas element 1 is giving a different value of u. So there is no continuity of u across the element when we go from element 1 to 2. So it's a incompatible displacement. These 2 elements are going to be incompatible, will not give continuous displacement distribution when we go across this edge. So this is what I wanted you to discuss, and of course we had discussed about the continuity requirements, considering different elements. I think the question number 4 is straightforward extension of what we had discussed as heat transfer problems. Only thing, the difference is that this is a membrane problem. Membrane means it is stressed, so there is a tension applied already there, and that is a known tension physically. Even if you don't understand, I think it should have been based on the differential equation, and many of you have, of course, have done that. So this tension is given like this. This is in plane tension, and then there is a transverse load Q. So for that, the differential equation was given, and I had asked you to develop the element level governing equation for considering a 3-noded triangular element. So differential equation, weighted residual statement, big form, and then integral functional, or from there you can develop the element level governing equation. So that is what I had discussed. So this was, of course, straightforward. This is physically the problem is like this is because of the weight of this rod, it has some in-plane tension, although in this case there is no tension in the other direction, so we have to differentiate Tx and Ty, and then if you apply a transverse load, so you want to then solve the problem. So this direction, I think it touches the wall but the board, so you are applying a load like this, it has already a in-plane tension or a transverse load, you want to study how it is going to deflect, and of course you can also look at the stresses. So that was the problem, the question number 4. So the differential equation was given and you had to set up the element level Gauss equation. So the differential equation for this was given as del by del x of t into del w by del x plus del w by del y t into del w by del y plus q equal to 0. So this was the differential equation where w is transverse displacement, that is displacement transverse to this, like in this case w is the displacement in this direction, t is in the in plane direction transverse displacement, and the load q is in the transverse direction. So this was anyway, if you look at this is exactly what we had discussed as heat transfer problems, only thing is physically the problem is different, otherwise the differential equation is of the same format. We had discussed this, so I expected you all to actually do this. Then question number 5 was to evaluate this integral. So this I know includes actually all the steps involved in isoparametric formulation, particularly when you want to evaluate the stiffness matrix using the Gauss quadrature numerical integration. So I just asked one term, so I had said that evaluate this integral -1 to +1 del n1 by del x whole square determinant j, d is high and d eta. And I had given you the element is actually a square in the physical coordinate space. So these coordinates are 0 0, this I had given as 4 0, this is 4 4 and this is 0 comma 4. So this is say node 1, node 2, node 3, node 4. This is because it was given that's an isoparametric element, so it is mapped to natural coordinate space to a square xi and eta, where this is again node 1, 2, 3 and 4. So obviously because you want to evaluate this integral, first you have to have the expression for del n1 by del x in terms of xi and eta, expression for j in terms of xi and eta, and then use the numerical integration. And now to have the j and even del n1 by del x, you need to evaluate your Jacobian, then inverse of the Jacobian, then express your del n1 by del x, and then do the numerical integration. So that is what was expected. I think this is straightforward, you can look at the solution. So first you write your x, so obviously these are the x1, x2, x3, x4 coordinates. So x is x1 is 0, like we write it as ni xi summation over I going from 1 to 4. So as you see the x coordinates of only node 2 and 4, they are non-zero, so which are actually 4 and 4. So this is going to be simply 4 into n2 plus n3, and this you will find when you put the expressions for n2 and n3 for 4 noded isoparametric element and simplify, this comes at 2 into 1 plus xi. n2 and n3 are safe functions, n1, n2, n3 and 4. Similarly y is summation over I going from 1 to 4 and I equal to 1 to 4, and this if you look at now y coordinates of only node 3 and 4 are non-zero, so this would be, and there are 4 basically, 4 here and 4 here, so 4 into n3 plus n4, and when you sum this n3 and n4 you will find that because in defining n3 and n4 you will have this 1 plus eta thing coming, so this would be 2 into 1 plus eta. Once you have this, see it's just few one more step in between, and then you come to this expression. You can even directly write it, or you don't know, you just do one step in between, expressions for n2, n1, n2, n3, n4, you can come to that. Then j is del x by del xi, del y by del xi, del x by del eta, del y by del eta. I think in the back side of the question paper I had given j, thinking that if someone forgets what are the expressions for Jacobian. So now del x by del xi is obviously 2, and del y by del xi 0, no xi term here, then del x by del eta is 0, and del y by del eta is again 2. So this is your j. Determinant of J is obviously 4 here as you see, and the J inverse is going to be 1 by determinant, and then you interchange these values. So 2, again these are 0 0, so 0 2, which would be actually simply 1 by 2, 0 0 and 1 by 2. This is the Jacobian inverse. Now how do we evaluate del n1 by del x? That is J11 star, this term is J11 star into del n1 by del xi plus J12 star into del n1 by del eta. So you need to spend some time to understand things. It is not that just before the exam, so try to look at. Some of you actually didn't evaluate this correctly. It's actually very simple expression, but you made it complicated because you didn't evaluate Jacobian correctly, or if Jacobian is correct, some of you didn't evaluate finally this expression correctly. So see here J11 star is 1 by 2, and into del n1 by del xi, if you look at the expression for n1, which is 1 by 4 into 1 minus xi into 1 minus eta. So del n1 by del xi is going to be simply minus 1 by 4 into 1 minus eta. And since J12 star is 0, so we don't worry about that. So it's just 1 minus 8, 1 minus eta. And now you put all of this in the integral. So that is integration minus 1 to plus 1, minus 1 to plus 1. This is 1 upon 64, 1 minus eta square. J is into 4 and d is high d eta. So this is, and then now we can of course take 4 by 64 as 1 by 16, minus 1 to plus 1, minus 1 to plus 1, 1 minus eta square d is high d eta. And then you now represent this. I had said that use basically 2 integration points along xi and 2 integration points along eta directions. So you represent it by double summation. Say I equal to 1 to 2, j equal to 1 to 2, and this whole of the function 1 minus eta square evaluated at xi I, eta j, wi and wj. Then no, this is going to be 4 terms. You evaluate this, finally it actually comes out as 1 by 3. There are 4 terms, you have to sum them and write it so that you can. So this was, so see why I asked this question was, you see it involves your interpolation for x and y, then it involves your Jacobian, it involves your Jacobian inverse, then how to evaluate the derivatives of the shape functions, and then how to do the integration. So, and we had discussed all of this actually in the lecture classes. So this was question 5, and then the question number, of course you would need some more time to evaluate of course all of these. So then the next question was question number 6. Question number 6, maybe I could have made it a bit simpler, because actually I wanted to test assembly including the reaction forces, but then I think at that time I thought that let me take a linear distribution of the load. So see, what I had asked was only the load vector, and this edge is fixed and this edge is subjected to a distributed force. So this is the distributed force. The maximum value here is 10 Newton per meter. This is force per unit length, and here it is 0. The global node numbers where this was 1, 2, then this is 3, 4, and this was given as 5 and 6. This was element number 1, element number 2. So see, this is already a known force acting on an edge, whereas this end of the problem is constrained. Again, if you look at the dimensions, I had given this again as 10 meters, and these 2 element lengths were this was 5 meters, this was also 5 meters. Load is in the in-plane direction. The 2 dimensions are comparable. Of course, no mention about the thickness here, but this dimension and this dimension is comparable. So obviously it cannot be a 1D. We cannot approximate it as a 1D problem. It has to be taken as a 2D. So plane stress or plane strain depending on the thickness. So but for the purpose of load vector calculation, that doesn't matter. So one is that you have to consider it to be a 2D element, and then I have also said that for the finite element mesh of 4 noded isoparametric elements shown, calculate the assembled load vector. So here what you wanted is to calculate the assembled load vector. So that was the question. So now the assembled load vector will have contribution from first element, will have contribution from second element. Now in each element you have one side this distributed force, another side you are also going to have reaction forces, distributed reaction forces on this edge here as well as here. Of course the reaction forces are unknown, so you will have to put them as finally the unknown forces. So if you wanted to calculate the F due to known external force, so for if you look at the element number 1, only want to consider the contribution from 2 to 4. So contribution to F are for the element for edge 2 to 4, although it has also contribution from this edge. So if you wanted to write this, it's the integration from 2 to 4. Now how do we write? It's again a 2D problem. So we will have two displacements. So when you consider the potential, it is going to be UV transpose into Fx Fy. Since Fy is 0, so it's only Fx. So if you look at it, is this load vector is again integration from edge 2 to 4 here, if I look at in terms of node 2 and 4, and this is H transpose, and the load distribution along x direction. Now it's a linear function of y, as you see here. So if I take, let us say physical coordinates x and y here, so this is here the y coordinate is 10, load is also 10. So load is load intensity is varying as 1 Newton per meter square. So you can say the load along the x direction is essentially y, and along y direction the load is 0, and then integration ds. And here, since the second is 0, so finally you would see that this integration 2 to 4 H transpose again is a 4 noded element. Now if you look at your H, we had discussed this is going to be N1 0, N2 0, N3 0, N4 and 0, then 0, N1, 0, N2 and so on. So when you take that H transpose and multiply with this Y, finally this will reduce to N1 into Y 0, N2 into Y 0, N3 into Y 0, N4 into Y and 0. This is ds. Again see this integral is to be evaluated from here to here. So now these are local node numbers. You will also have local node number, say local node number here 1, this is local node number 2, this is local node number 3, this is local node number 4 for the first element. So along edge 2 to 4, that is local node 2 to 3, you only have non-zero values of N2 and N3. N1 and N4 are the shape functions corresponding to this node and this node. So they will be 0. Now you can of course cross check from the expressions for the shape function. So then finally what you need to evaluate is 2 to 4, and these two becomes 0, then you have N2 non-zero, so whatever it is N2 into Y 0, N3 is non-zero, so N3 into Y 0, and then 0 0 ds. And now the evaluation part comes. So you have to obviously write here N1, N2 and N3 of course are in terms of xi and eta. Along this edge, if you look at here, xi is actually, each of these elements are going to be mapped to a square in the natural coordinate space. So along this edge, your xi is going to be +1. So it's only eta which is varying. So if you evaluate these shape functions, they are already only in terms of basically eta, and you also need to write y in terms of xi and eta. So for that you need y again, y is equal to ni yi, and you will see that similar to the previous problem which I just discussed, this is going to be length of the element along y direction is phi, so half of that is, so this would be 2.5 into 1 plus eta. And again if you look at here, as far as x is concerned, x is going to be ni xi, and if you see element is a rectangle in the physical coordinate space, so this will be phi into 1 plus xi. If you look at for a constant xi, x is constant, so dx is 0. So if you see that ds, the ds is simply going to be actually dy, and which is going to be 2.5 into d eta. It's actually square root of dx square plus dy square, but along this edge your xi is constant, so that means x becomes constant, dx is 0, so then ds is dy equal to 2.5 into eta. So finally you will see that now this load vector reduces to, so your f for the element along h2 to 4 would reduce to eta going from -1 to +1. Now everything is written in terms of eta. Then you have 0 0, that is the first two terms, then n2 into y. Now what is the expression for n2? N2 is 1 by 4 and then 1 plus xi into 1 minus eta, and xi equal to +1 along that edge, so you will have this as 1 by 2 into 1 minus eta. So this is n2 into y, n2 is already 1 by 2 into 1 minus eta, and then into y, which is also 2.5 into 1 plus eta, because that's this term. So if you look at 0 0, n2 into y, then again 0, n3 if you look at, n3 is going to be 1 by 2, 1 plus eta. So you can look at that 1 plus eta, and into y, which is again into 2.5, this is into, so 2.5 into 1 plus eta, and then rest is 0 0. And now ds is dy, which is 2.5 into d eta. So 2.5 you can say right here, and d eta. And then do this integration. Now there is here no mention whether you should evaluate this integral numerically or explicitly. So obviously it is easier to do the explicit integration here with respect to eta. So you just integrate this, and you have the load vector due to distributed force for the first element. So this integration you can do. Now when you go for the second element, so that is element number 2, and for element number 2 again you have to consider here, I will come back. So for element number 2, this is local node number 1, the way we considered earlier. This is 2, this is 3, and this is 4. So same way you would see that Fe for the second element due to distributed force, again ds is going to be same, 2.5 into d eta. So that 2.5 you can keep here, and then this is -1 to +1, and the same thing that only n2 and n3 are going to be non-zero, so the first two terms would be 0 in terms of local coordinates, and the values of the shape functions are also going to be 1 by 2 1 minus eta and 1 by 2 1 plus eta for second and third nodes of the second element in local node numbers. So this would be 1 by 2 1 minus eta into y, of course has to come 0 1 by 2 into 1 plus eta, and then of course 0 0 0, and then into y. Now y for the second element you have to write, because now if you are using the origin of y coordinate here, or if you take the origin of y coordinate here, then the value of q here is non-zero, so you can do either way. So the y coordinate at any point here is going to be actually this phi plus local y coordinate within the second element, so you can write either way. So here you will have in addition your y, and of course this is d eta, same way what we have there, and y is going to be phi plus, you actually again n1 y1 plus n2 y2 plus n3 y3 plus n4 y4, put the appropriate values of y1 y2 y3 y4, you will get y as phi plus 2.5 into 1 plus eta. So you just have to put this value here, do the integration with respect to eta, you get the load vector for the second element. Now finally the assembled load vector. So the assembled load vector is going to have contributions. So this is what you need to do, first step, that is due to given a known load, what are the contributions to load vector, first element, second element. Once you have done this, this is actually straightforward. And then no assembly. When you look at the assembly, it has to have contribution due to the AF external you are calculating because of this distributed force from here to here as well as here to here. In addition, at node 3 and 5, global nodes 3 and 5, you will have reaction forces. Those are from the distributed reactions on this edge. So if you look at finally the assembled load vector F, So this will have how many elements in it? What would be the size? Because there are total how many nodes? 6, and at each node we have 2 degrees of freedom, so it's going to have 12 entries. Now the sequence would be in terms of global node numbers. So if you look at the first global node number is the corner node here, and you expect to have 2 reaction forces, because it is constrained to move both, it is not allowed to move along x and y directions. So you will have corresponding reaction forces, which would be actually the integral along this edge of the unknown distributed reaction here. So we can represent that by concentrated reaction force. So say you can maybe want to say that as F1x and F1y. Then the second node will be having contribution. Your second node is here, and this is coming from the contribution to the load vector here is coming from the first element, and that is nothing but actually from this load vector. So this does not contribute anything to the first node. The second node would be some non-zero value. Let me for the time being just say that this value is F1 and this value is F2 after doing the integration. So what you will have here is, next is F1, and along the y direction there is no contribution because this term is 0. So when I am adding there, this is going to be 0. Then you come to the third node. Third node is again, if you see, I have to go too many times here. So 1, 2, global, this is global node number 3, no this one. At third node 3, because it is not allowed to move along x and y direction, you will have 2 reaction components, and which is going to be basically the contribution from this side and as well as this side. So you can finally say write that as at node 3, so it's say F3x and F3y. Then node 4, global node 4 is having, that's a global node 4 here. This will have contribution to the load vector from this as well as this element. So one contribution is this actually F2, and of course along y direction is 0. So let me call this integral as say F3 here. Finally this after integration, let us say this is F3 and F4. So this will come out here as actually F2 plus F3 and then 0, because y direction there is no load. And then come to node 5. 5 again is not allowed to move along x and y direction, so you can say F5x, F5y. And then finally node 6, where you have contribution from the second element, so that's actually your F4 and 0 of course. So that is F4 and 0. So if you look at you will have to look at local to global connectivity, that degrees of freedom corresponding to local element node numbers and global node numbers. So finally here you are going to have summation, which is corresponding to the total force at node number 4, which is common to both the elements, and other places either you have reaction forces or only contribution from the first element or contribution from the second element. So this was the assembled load vector. Okay, so this is what I expected you to do. Yeah. Actually, since I had mentioned that 4-noded isoparametric element, so I expect you to do that. Of course, you can also do the formulation. If that was not there, then you could have calculated the load vector using formulation in physical coordinate space, using shape function in terms of say x and y. So that was possible, but here I had said that 4-noded isoparametric element. Of course, what I could have done is that given this load constant and asked you to use lump load vector, so then I could have just tested assembly, which was actually my main aim, but I thought that you also should do some calculations. So that is why but I think I realized later that I could have given this as a uniformly distributed load, and you could have asked you to just use the lump load vector, so that then you just do the assembly. That is coming from here. So if you look at as I said, expression for y is this, expression for x is this. You are going along this edge where your xi coordinate is constant. So x is constant, so dx is 0. So then ds is only square root of dx square plus dy square, which is just dy, because dx is 0. So, the square root of dy square is simply dy, and then dy is from this 2.5 into d eta if you differentiate this. Yeah. Yeah. Right. Here also along one edge, but this is acting on two elements. So that's the only difference. And this is isoparametric formulation, that there you have a choice to either use isoparametric formulation or the formulation in the physical quantity space, that is using area coordinates L1, L2, L3. Yeah. Yeah, so that's what, no, the y coordinate is actually the load is if you use the, so the question here is about the load distribution. So if I use the global xy coordinate origin here, so then whether I am in the first element or in the second element, load is equal to y. But then y, because here, no, if you look at for the first element, here y coordinates are 0, comma 5. The coordinates of this node are 10, comma 5. The coordinates of this node are 10, comma 10. The coordinates of this 0, comma 10. So when you write your y as n1 y1 plus n2 y2 plus n3 y3 plus n4 y4, your y for the second element will come out as actually this, and that has to go in here. Okay. Yes. So yeah. So here the thickness is already multiplied with the load. So see this force is per unit this length, this length. So the thickness is already multiplied in this. You know, if you talk in terms of Tnx, so here Tn, you know, whatever load is there, this is Tnx into thickness. So then it becomes per unit this length. Okay. So should I discuss the last question? I think some of you have the CFD class, I think probably, so I always exceed, but let me, I think I don't want to drag it for the next class. Question number 7 was the easiest one, but see if you, what I had said, there was one horizontal member and there was one vertical member. It was fixed here, it was fixed here. I had also given the transformed stiffness matrix on the second page of the question paper. Should you need not do any transformation. This is node 1, node 2, and this is node 3. Only thing, see, I had made a statement that the joint between these two elements, so this is element number 1, this is element number 2. Joint between these two elements at node 2 is a pin joint. So pin joint means they can have a relative rotation at that point. So then theta for the node 2 belonging to first element and theta for node 2 belonging to second element would actually be different. So if you make theta 21 equal to theta 22, then there is no relative rotation possible. No, the joint has to rotate like that. But once there is a pin joint, and I had said that no, there is a relative rotation between the two elements at node 2, so they can have different theta. So when you do the assembly, what I expected you to actually just take into account that. So if you look at now with that concept, keeping in mind the relative rotation at node 2 between the two elements, of course you will have displacements and rotations at node 1. So say capital U and V at node 1. So this is U1, V1 and theta 1. Then at node 2, but see the node 2 has to translate by same distances along x and y direction, whether it is belonging to first element or second element. So U and V are the same for both the elements. So U2, V2. But there would be two thetas, one for the first element, one for the second. So theta 2, let's say for the first element is theta 21. Of course you can put these degrees of freedom anywhere you like, and then there would be also a theta for at node 2 belonging to second element. And then of course the third node, which is U3, V3 and theta 3. So now your stiffness matrix is going to be, rather than 9 by 9, would be actually 10 by 10. So the first element contributions would go to 1, 2, 3, 4, 5 and 6. First 6 rows and columns, whereas when you add the second element contribution, that will go to 4th, 5th and then this 7th, 8th, 9th and 10th rows and columns. So in the corresponding rows and columns, same thing on the right hand side. So this is what I expected in this last question. And the purpose was to just check this part of assembly, that is, should recognize that there is a different theta. And in fact, in some class in the discussion, I did discuss some problem like this, where there is a pin joint and then how to handle that. And of course, then finally, because these are 0 and these are 0, so when you take the 4th, 5th, 6th and 7th equations, you can solve for these unknowns. There were forces given, external forces at node 2. So okay, so this is what was minor 2 question paper. It was maybe another 10 minutes more, so but still I expected you to do at least whatever questions you do it more correctly. So that means if you have not done well, and I think the average is not good this time, that means you have not actually studied thoroughly. So you have to spend some time after the lectures. I keep telling you, if you have any doubts, questions, you ask, but you don't ask. Okay, so with this I conclude today's class. Actually, today I have to go to I have my wife from doctor's appointment. So if you have any doubts, you can ask me.